vector machines, it can be used for both classification as well as regression at a very higher level. Okay. So what we want to do after this unit is to be able to identify support vectors within a data set. Okay. And then we should be able to explain what a decision boundary is. And then we'll look at various kernels, okay, or applications of SVM. And then hard and soft margin. And then we'll look at linearly separable and non-separable cases. And then we'll talk about the kernel tree. Okay. All right. So mainly the support vector machine is, like I just said, is one of the classifiers that can be used to make predictions. Okay. It learns, it's also a supervised machine learning. Okay. It learns from the system as you train it, and then it's able to make predictions. It receives input into the system, and then this input is subjected to various applications depending upon the nature of your data set. All right. And then it's able to make predictions. All right. Able to make predictions. So we'll look at various terms that are associated with support vector machines. Okay. So SVM basically is based on the idea of finding a hyperplane that best divides a data set into classes. Okay. So the concept of SVM is that there are several ways by which we can divide a data set into regions whereby we can make predictions. Okay. So it's to find the hyperplane, okay, or should I say a separator, okay, that best divides the data set into classes. All right. Okay. So in order to do that, there are some terms we need to understand. Okay. We have what we call support vectors. Please, can you all hear me? Can you all hear me?
Yes, sir.
Okay.
Yes, sir. We can hear you.
Yes.
Good. So we have what we call support vectors. Okay. Support vectors. And these are data points that are nearest to the hyperplane. So if you see the diagram on your left, we have one of the green circles being close to the hyperplane, okay? And one of the blue is also close to it, all right? So these support vectors, when they are removed, can alter the position of the hyperplane, okay? Let's say a data point that is very crucial. When you remove that data point, okay? For instance, it can severely alter the, how do you call it? The properties of the data set, okay? Especially if that data point has a very great influence, okay, in the whole data set. All right. So these are what we call critical elements of the data set, okay? And we call them support vectors, okay? We call them support vectors. So the idea behind support vector machine is to create a hyperplane, okay, which doesn't have so many support vectors very near the hyperplane. Because if they are very near the hyperplane, they affect the predictions that will be made. So as much as possible, we want it to be clear so that if all the variables are not very near the hyperplane, so the further away they are from the hyperplane, the more we are confident in our predictions, okay? But if they are very near the hyperplane, we can misclassify some data points, all right? So as much as possible, we want to find the best hyperplane that, we can use in making our predictions. We don't want a situation whereby you have so many support vectors around the hyperplane and it causes problems in terms of your prediction. Okay. So, like we said, we have this, data points. Okay. There are so many ways by which we can divide these data points in order to make predictions. Okay. All right. So we see that we have 1, 2, 3. So here, there are 3 different ways by which this can be divided. But what is the best way to do it? Okay. That is the issue here. What is the best way to do it? So it depends upon your data set. And one thing that the support vector machine is able to do is to look at the content of your data set and is able to use appropriate algorithms to be able to make predictions, okay? Because some data sets are what we call linearly separable, okay? And some data sets are not linearly separable. We call them non-linear separable cases, okay? So we'll get to that point, but the main issue here is that we want to find the best hyperplane that is able to divide your data sets into regions in order to make your predictions, okay? So if you see the first hyperplane, for instance, the one that slopes diagonally to the right, okay, you see one is straight, one is going down, okay, to the, okay, let's say one slants to the left, one slants to the right, and one is right in the middle, okay? So the issue is which one is the best way to separate them, okay? If you look at the one that slants to the right, you see that it has these 2 points very close to the hyperplane, okay? We don't want things like that, okay? If you look at the one that slants downwards, okay? Downwards to the right. It also has 1 point here that is very close to the hyperplane, okay? We don't want things like that. But if you look at the one in the middle, you see that it's quite far from both classes, okay? So that if you are using the one that is vertically running through to make your predictions, you are confident that whatever predictions you are making, okay, will be correct. But the one that is very near the hyperplane, if you make a mistake, you can misclassify it and it might come to the other side, okay? So that is the main point here, all right? So this is just for your information. We have what we call a decision boundary, okay? So normally you can have one that is upper and one that is lower. So you see the dotted lines, okay? The distance between the dotted lines, the one that is up and then that is the one that is down, we call this the margin, okay? Here is the margin, okay? And we have the boundary here, and in between here is the margin, okay? So what you want to do is, as much as possible, don't create a situation whereby you see, can you see my cursor?
Yes.
Yeah.
Okay. Okay. So you see that this lower plane, for instance, you have a support vector here. It's on the line. Okay. There is another one too here on the line. Okay. And there's another one too here on the line, the x. So we have x plus, s minus. Okay. So all these are on the line. These are support vectors. Okay. As much as possible, we want to avoid that. Okay. We want to create a margin which is clear of all the points. Okay, which is clear of all the points. Okay. So we have some mathematical This is just to show you the mathematical relationship between the points. You don't really need to worry yourself too much with that. Okay, but for those who are interested, this are the weights multiplied by the value of the S plus the bias. Okay, so the middle one should basically give you 0, and then the upper one gives us 1, and then the lower boundary gives us -1. Okay, so in between the lower boundary and then the upper boundary, okay, this is where we have what we call the margin. Okay, so what we want to do is to choose the maximal margin, okay, hyperplane, so that we minimize classification errors. Okay, all right, and we have what we call soft margin and then hard margin. Okay, so when you have a very wide margin, okay, you have a very wide margin, and then all the points are separated, okay, from the upper and then from the lower, we call a soft margin. But sometimes you can have a situation whereby the dotted lines, both the one at the top and the one at the bottom, are very close to the one at the middle. We call it a hard margin when you have a situation like that. Okay, so the idea here is to have the maximal margin hyperplane. Okay, so that there isn't something that is in between here, or even the support vectors that are near these ones are kind of, you know, you take them off so that it doesn't affect your predictions. Because something that is here, for instance, if you make the least mistake, you can predict it into another region, and you don't want to do that. Okay. All right. Any questions so far? Okay. All right. So here, for instance, so we have a situation where we have sometimes when you have a linear separable case, okay, you see the square data points and then the round data points. Okay, so just a straight line, okay, can separate the two. Okay, so this is a typical case of linearly separable case. You can separate them, you know, okay, when you draw a straight line, okay, across them, you can separate the two. But it is not all data sets that are linearly separable. Some data sets are nonlinear separable cases. All right. So in such instances, if you use the linear to classify it, okay, you will make errors. So here you see that this is a typical case of non-separable case. Okay, so you see some of the square data points. You find them at the region of where you have the round data points. Okay, so in this case, if you are to use linear, okay, a linear function kind of to separate the two, you will misclassify this data point. Okay, you misclassify this data point. Okay, so here you see that some round data points are also here, okay, where you have many of the square data points. You have round ones here, and then where you have the round ones too, you have some square ones here. All right, so these are error points. Okay, if you are to use a linearly separable function to do the separation, okay, you can misclassify this. But the good news is that with SVM, you are able to use various ways by which you can deal with linearly separable cases and then cases that are not linear or non-separable cases. All right. we'll look at all that. Okay. So within the SVM, it has what we call kernels. Okay. So kernels are like the functions that support vector machines uses to kind of separate or classify the data points. Okay. So if you have a nonlinear case, okay, SVM is able to create something like this, okay, where it is able to classify the X from the zeros, so to speak. Okay. We will come to this later. It does this transformation through what we call the kernel trick. Okay. But first of all, let's go into R and then see how we can apply SVM. Okay. We can apply SVM and then be able to interpret the results that the model built. Okay. So before we move on from here, where we can use various methods or kernels of SVM to deal with linearly separable cases and non-linearly separable cases. Let's first of all see how a typical SVM works, okay, and then how we can interpret the model, okay? So let's go to our studio. Okay. Just a minute. Okay. So let me share my screen. Oh, I already shared. All right. Please, can you see my screen now?
Yes, sir.
Okay, so first of all, let's do our installation. Okay, let's install the package that is used for support vector machine. So we use the E1071 package. Okay. E1071. Okay, so when we are done with the installation, then call it from the library. Okay. So please, when you are done, let me know. If you are done, let me know in the chat, please. Okay. Okay. Good. All right. So let's generate some random numbers, okay? Then we'll work with that. If there is time, then we can take a raw data set and work with that. So let's generate a data frame with two predictors. So we have x1 and then we have x2. Yeah. So let's specify the number that we want. We want 200. Okay. Oh, sorry, let's set the C so that we all get the same result. So let's create our data frame. So data.frame. Now, for you to understand this, let me start with this. So we want to create some random numbers, okay? 200 of those, okay? So we want to start with x1, okay? And then we want some random uniform numbers, okay? So we use a run if. Okay, so to generate this random numbers for us. And then we do the same for x2. So random. So what we want to do is, I'll bring this one here. So what we want to do is that all this should be a data frame. Okay. So we put it in a data frame. The data.frame. We wrap it around this random number. Okay. And then let's call this df. Okay. So now we want to create, let's create two classes. Let's create two classes separated by a straight line, decision boundary. Okay. Separated by a straight line. So let me put the straight line here. A straight line decision boundary. Yeah. So in other words, we want a situation where x1 is equal to s2. Okay. So it will be diagonal. Yeah. So if we are going to have two classes, one will be up, one will be down. Okay. So let's map the x. Okay. One of them, x1 can be mapped to -1. Okay. And then one of them too will be mapped to 1. Okay. So on the y-axis, we take our DF data frame on the y-axis. Okay, what we want here is that our DF
I don't know.
yes.
Why are we putting Y?
Okay, so we want to the line probably let me finish the code and then you understand.
Okay.
So here we want to create let's use an if else situation here. So if else, we take the data frame, okay, x1, okay. So if x1 minus x, if the difference between them, if there's a difference between them, this one s2, okay. If it is more than 0,
$.
okay, then it should either fall in this region of -1 or 1. Okay, and this -1 or 1, it's not really a number. Okay, it's a symbol. So let's factor it. Okay? It would make much more sense when we plot the graph. Okay, so let's factor
Okay.
this.
Shouldn't there be a $ for x2? DF x2.
Yes. Thank you. Okay, so let's specify the levels. Okay, so the levels we have -1 and then 1. Okay, right. So let's run this. So we can visualize what we've done. So let's use ggplot for that. All right. So let's ggplot df. Okay, our aesthetics. We have x1. Then we have x2. Okay. Y. So it will give us what the scatter plot. So let's use the geo point. So let's color them. Let's color the points so that we can separate. So let's add the scale color alone. This one. So let's specify the values. So it's a vector. We have points that are -1. Let's assign them, all of them, to red. Okay. And then one, let's assign them to blue. Okay, so let's put this a bit. Let's bring our plus sign here. Add another layer. So we want the diagonal line to go across it. Okay, so let's use the geometry AB line. Okay, remember that x1 is equal to s2, so the slope is 1. Yeah. The slope is equal to 1. And then it starts from our intercept. Okay, so we can name all this P. Yeah, I think we are okay. Data point, aesthetics, geo point, colors, diagonal line. Okay, all right, let's run this. Good. Okay, so we can plot. Let's see what we have here. Okay, so we have here we have 2 classes. Okay, so we have 1, 2, all right, and 1, 2, the left. Okay, so we have those that are above the AB line, okay, and then those that are below it. Okay. Are we getting the same plot?
Yes. Yes.
Okay. So now let's create a margin. This one hasn't gotten a margin. So what I'm doing now is I'm just using ggplot to explain, and then we use support vector machines algorithm also to build a plot. Okay, so we want to create a margin here. Now you see that some points. Okay, so this you can call this decision support vectors. Okay, some points are very close to the AB line. Okay, or the decision boundary. So the decision boundary is what separates the two. Okay, yes, yeah. Yeah, your hand is raised. Wait, are you asking a question?
Yes, Nana.
Yeah, please go ahead.
I'm getting an error.
With your what? With
the plots.
Have you called ggplot from the library?
Yes, it's saying that error in scale color manual. Continuous values applied to discrete scale.
Did you factor the -1 and then 1?
Yes.
Okay. Okay, share your screen. Let me see if probably there's something you are missing.
Okay.
Okay, enlarge it a bit so that we can. Hey, yeah, your fonts are very small. Can you see?
Yes, sir.
Wow. Hey, increase them a bit. Appearances, yeah, and then increase the font a bit. Some of us, we can't see that.
The font around 12.
Oh, I see. I think probably is
The screen size, the resolution.
not the screen
Oh.
size. The font type.
Oh, okay.
Yeah. So probably you might want to have a look at it. So yeah. So he's saying that error. Why is the error?
Yeah.
Color manual. Let's see. I'm trying to read through your code.
Okay. Was I supposed to bring a bracket here somewhere? Or
Where?
that place is okay?
The
if else.
I think that's okay.
Yeah, inside your levels, it's 1 and 1. Shouldn't it be negative 1
Yeah,
and
yeah.
1?
Yeah, you have 1 and
Okay,
1.
it should be negative 1 and 1 instead of 1 and 1.
Yes, because at the top you
Yeah.
have -1 at the top.
Yeah.
Exactly.
Okay.
So run it again.
Thank you.
Try that, let's see. Yeah, what I not so chance.
Yeah. Thank you, Nana.
It's working.
Thank you,
Okay.
Nancy.
All right. So right. So let's screen again. All right. Okay. So what we want to do is to create a decision boundary. Okay. Create a margin. Okay. We don't have a margin at the moment. So let's create a margin. Okay. So we can set a value. Okay. We can set a value and then deduct the value for those at the top and those at the bottom. Okay. And then it will create that margin for us. We are doing this manually. Okay. So let's create margin. Okay, so let's set a value. You can call it data 0.5. Okay, so let's adjust. Okay, so what we want to do is to create one. We'll create one at the top of the AB line and one also below the AB line. Okay, so that we can have in between or with nothing there, they will have the margin. Okay. So let's call it DF1. Okay. So what we are doing is to take the difference between 1 and 2. Okay. We take the absolute figure. Okay. We take the absolute figure and then we take DF(x1). Okay. Two. Okay. Have one that is about the delta. Okay. Now, what we have to do here is that everything that we are doing, okay, we are taking it from the DF, okay, the main data set. So we are creating a subset based upon this condition. Okay. Okay, so we have DF. So let's look at the number of rows for DF. Okay, that's 200. Let's look at the number of rows for DF1. Okay. So as a result of applying this adjustment here, okay, we have created another one for DF1. Okay. So now let's replot our new data set. Okay. Let's see.
Yes, sir.
Yes.
Is it possible that my DF1 can be 200 as the DF?
No. Did you bring the minus sign here?
This way. Is it line 25 and 26?
Yes.
Yes, please. The minus sign is there.
It's not equal to.
No, it's not equal to, it's minus.
Okay. Did you run the delta 0.5?
Yes, please. I
0.05.
did run it. Yes.
Okay. And then let me have a look at your code.
All right, sir. Yes, sir. Can you see it now?
Yes. Okay. So no, your delta, you've made it negative 0.5, like 28. You run it again.
Okay, thank you, sir.
So let's replot our replot. So you need to understand that since we are using the absolute figure, it does it for above the AB line and also below it. Okay, so it's 0.5 above and also 0.5 below. Okay, for the delta. Okay. All right. So let's replot our new data set.
Hello, Nana.
Yes.
I'm also having 200 for the DF1 and then, but when you were explaining to Christy, I think I lost.
Okay. So did you set your delta at 0.05? Or you made it negative 0.05?
Yes, I made it negative 0.05.
It's 0.05. It's not a negative.
Okay. Thank you.
So let's replot our data set. Okay. Okay, so let's do a ggplot. A ggplot. It's still the same thing, just that this time around we are taking it from DF1. Okay, so let's copy what we have here. Let's copy this guy. And now we made this one DF1. Okay. Okay. So, all right, so let's look at our new P. Okay, so you see that now the data points that were very close to the uh, to a decision boundary. Okay. Okay, we have removed 20 of them. Okay, so that's how come now we have 180. Okay, right. So we've created some space. So let's add some dashed lines to the top and also to the bottom so that we have our margin. Okay. So let's plot our margin boundaries. So we are taking everything here and then we are adding AB lines just at the top and then at the bottom. Okay, so let me start with our P. Okay, so let's add a geom line. Geom AB line. Our slope is equal to 1. Our intercept is equal to the delta, isn't it? Which is 0.05. Okay. So let's specify our line type to be dash. Okay. Let's copy this and then we do one for the line above. So this one was delta at the top. So we add the same thing. Now the delta we are using, okay, because it's coming below, should be negative delta, isn't it? So that it will come below, but everything stays the same. Okay, let's name everything Q. Let's give it an object name of Q. Okay, let me bring this here so that okay. Let's run this. Let's start up here. So now you can see the decision boundary. So what we'll be doing is that, so here, see that when we plotted, we still have some points that are very close to the decision boundaries, okay? So like I explained earlier on, these are what we call support vectors, okay? Now, when we apply the SVM model itself, it tells you the number of support vectors that are available that are available in the data set. Okay, and then it gives you some tuning parameters to be able to control it. Okay, so that you can have a more effective model. Okay, so let's do that. But before we do it, let's split our model. Let's partition our model. Okay, and then we fit it into the SVM model. Okay, so this is just to give you an idea as to how the decision boundary can be plotted using the ggplot. Okay, now let's partition our data set and then we go on to fit the model. So basically, this is what the our data set is. Okay, the random figures that we generated. This is how they are separated. Okay, so this is a linearly separated case. Okay, because we are using a straight line to separate both of them. Okay, so this is a linearly separated case. All right. Okay, So let's partition our data. Okay, so since this one is a random uniform numbers we generated, let's see the ones we generated. Let me run. Let me run X1 and then X2. Okay. Sorry, put it all together in the data frame. Right? So we are seeing, so these are the numbers we generated, okay, for DF. Okay. So the random uniform numbers, we are normally between zeros and one, okay, between 0 and 1, right? So these are the numbers, and then we also associated with the region where they were. So these have been randomly done. Okay. So because they are between 0 and 1, I don't think there are some properties in there that so we can use another split to do it. We don't necessarily have to use how do you call it, initial split. Okay, since all these are between zeros and ones, I think the properties will stay the same. Yeah, Nancy.
Nana, help.
You said-
First of all, you see
Yeah.
how your columns are labeled X1 and X2?
Mhm.
Mine is showing X1 ... runif.n, then X2 ... runif.n.
Mm.
And also my second plot is not plotted.
Okay, so there's an issue somewhere. Okay, let's
Yeah.
investigate. Share your screen. Let's see if you can share. Now you can share it, isn't it?
And
Just share the R1. We did it like we did it yesterday. Sorry, do it like we did it yesterday. Hey, Nancy, you two, your phones are small. Okay. All right, so let's
The
see.
second delta is supposed to be minus delta, not equal to delta.
The second delta should be is minus, is negative. That is the one that goes below. Yeah. Nancy, have you seen it? Can you hear us? I think she cannot hear us.
Nancy, you are muted if you are trying.
sorry, I was muted.
Okay.
Is it where my cursor is?
Yeah. So
So I should put
so put a negative. So one of the delta is negative. Yeah.
so right here is
Yeah.
okay.
Yeah.
Ah,
And then run it again.
I'm still getting that error.
Okay.
It's
so
saying
The same route.
so fix the following markings X and Y, but I don't have any X and Y specific X
can
and
you
Y.
can you increase your fonts a bit?
Yes.
Okay.
Yes. Please, I'm coming. Okay.
Okay.
Nancy, your geom up line is supposed to be 2. You've plotted for only 1. So copy
My
the
geometry line.
yes.
Your
This.
the geometry line, one is for positive and one is for negative. So the one
Yeah, I have two. There's one on
Yeah.
top and then there's one.
Two. Yeah.
okay. So the first one, was it negative or positive? Your delta.
The
Positive.
first one, it was just intercept is equal to delta.
Uh-huh.
And then
Good.
the second one, intercept is equal to negative delta.
Uh-huh. All right.
I'm sorry, I'm trying to make it big, but my thing has vanished
okay.
on the top.
Yeah, so you need to
Yes, yes.
Try control plus and minus. Okay, that should either increase or decrease your fonts.
Control.
control
Yeah,
plus.
control and then plus or minus.
Please,
So
can
plus
you
to
convert?
increase, minus to decrease.
Yeah, I beg you, can you convert this keyboard shortcut to Mac for me?
Please use command.
So it's the command.
Command. Okay. Thank you. Thank you. Please, is this better?
It's better. Good.
Okay. So which one should I modify? Because
Okay.
I have.
Let me read through your code.
Okay.
Okay. So for line 32, run line 32. Let me see.
All right.
That one is fine.
Yes.
Okay. So
This
from
is calling it is what you
okay,
say.
so you're having a problem with the margin boundary. So can you scroll
Okay.
up the 39? Let 39 go up. Let it go up so that we see. Okay, so you have here geometry line slope equal to 1 intercept delta. Line type that. And then intercept. Okay, so
Because the map is not coming. This one is also not coming.
okay, so run line 40, let's see. Is that where you are having the error?
The error is starting from my ggplot.
Okay.
Yeah, and because the
It's
ggplot is
starting
not
from the P. It's starting from the P.
exactly.
Okay. Then go to the one before this. Go to 20 something. Okay.
The end row.
Let me see.
Should I start running from this again?
Just a minute. So
Okay.
run your end row, let me see, for DF and then DF1. Okay, good. All right. Okay. So let's come to ggplot. So you have ggplot DF1.
Yeah, the aesthetics
And then
in
aesthetics.
geoplot.
Okay, do you know what? Put a comment on 34 and 35. Put a comment there. 34 and 35. Remove the plus from 33. Run this one alone, let's see. Okay, so run P, run 37, let's see something. Let's see if it will flow. Okay, so it's from there, right?
Yes.
Did you call ggplot from the library?
Yes, I did.
Okay, so let's call it again.
Okay.
You can put it under 30. Okay, fine.
Wait, ggplot 2 instead. I'm sorry.
So you see there was an issue here.
And try this again. And this again. Still.
Let me see.
But Nana, look at my titles for the X1, X2.
Yeah, that's fine. It's working fine. Oh, okay.
Should all of these be showing the run if?
Okay, so let me see. Okay, so that means I have a couple of issues. So let's see how you started with the run if. So you set a number for 200, and then you set a number for 200, and then a data dot frame.
It should be X1
That's
is
it should be
equals to
equal.
run if.
Yeah.
Not an assignment. Oh, right there, yes, someone.
Oh, you did an assignment.
Thank you very much. I'm so sorry.
That's all. So I think it's starting from there. So run it again.
Um,
So remove the comment and the others, and then run it.
Excellent. Thank you. Thank you very much.
Nana,
Yeah, good.
is her DF1 is now 179. Is it supposed to be so? Instead of 180.
Is that what she had? Okay.
Yes.
Yes.
Okay, so
It's
check your delta again. Just run it again and then see. Okay.
all right, Nana.
All right.
And the delta is still 0.05, right?
Yeah, 0.05. Yeah.
Okay.
Okay. All right. Good.
It's still 179.
It's still 179.
I think
What?
it varies. I had 185 as well.
185. Okay.
Yes.
What did you set your seed with?
100.
100. Okay.
Yeah.
No problem. It wouldn't make any significant impact on what we do.
All right. All right. Thank you very much, Nana.
Okay, so let's partition our data. Okay. So like I was saying, this is uniform numbers we've chosen randomly between 0 and 1. So I will not necessarily use the initial split. Okay, let's use another type of split to do the data partition. Okay. All right. So we can just use a sample function. Okay. So we take all our rows 1 to the number of rows for the DF1 function, DF1 data set. Okay. Now, what size are we going to use? Let's do a split of 80-20. Okay. So we take our number of rows for the DF1, yeah, and then we multiply it by 80. 0.8, sorry. Now we don't want to do sampling with replacement. Okay, so for the replace, we say false, so that the other 20 will go into our test data. Okay. So let's call this data split.
Please, can we see the replace equals to?
The replace should be equal
It
to
is 4.
false.
Okay.
All right, so okay, let me bring it here so that I can see. Sorry. All right, so let's set our train set. Let's run this. Let's set our train set. So we take our DF1, okay, and then we create a subset of it using the data split. Okay. All right. The subset is always a square bracket. Okay. So data splits. Okay. So all the columns remain the same. Okay. So that's our train set. And then let's use that for our test set. Let's copy the same thing. Remember that the train set is 80%. Okay. So the test set is just negative of the data split. That gives us the 20%. Okay. Okay. So we change this to test. So this one will be, we just made this negative. Okay. So that will give us the test set. So let's run this guy. So we have our train set and then our test set. We can just check our number of rows for test sets, for train sets, and then the test sets. And then let's do the same thing for our test set. You could also do a glimpse just to have a look at them. Okay. If you want to do a glimpse, then you need to call dplyr from the library. Okay. All right. So we have this. Okay, 180. Good. Now let's fit our support vector machine model. Okay, so we use a function SVM. Okay, so here, remember that we are predicting Y. Okay, let's have a glimpse of our data set. So we have S1, S2, and then Y. Okay, so it's the Y we want to predict. Okay, so Y is the outcome variable, and then the predicted are S1, S2 in this case. All right. Okay. So let's put these guys. we have our SVM, okay? So we are predicting Y, okay? So that everything, okay? Period dot. And then let's specify our data, okay? So if you want to know more about this, you can check the documentation, okay? SVM. Can check the SVM documentation from help. Okay. No, I don't know. Okay. So you can check the arguments from the documentation. Okay, we have data, formula, SY, scale, okay, type, okay, the kernel. So at the moment we are using the linear kernel. Okay, we'll look at other ones. Okay, all right. So that's just for your information. Okay, so let's look at, so it has taken we have specified the formula. Okay, let's look at the data. So the data, we are taking our train set, isn't it? Train set, we using it to train the model. Okay, and then we have the type. Okay, so we want to classify Y. Okay, so for SVM, we call it C classification. So C classification. Okay, and then you want to specify the kernel. So the kernel is the method. Okay, so kernel here, we know that the data set is linear. Okay, so let's use linear. Kernel is linear. And then scale. So we use this scale when you want to kind of normalize your stuff, okay? But for our purposes, let's use false. But in real world, don't be set to true. Okay, so we have our model. So let's call this SVM model. Okay. So let's see on this. So let's look at our model has run. Let's look at the components, what the model is telling us. Let's run the model. Okay, so we have some information here. So this is the SVM model, okay, and this is the formula we use. Okay, these are the arguments we set. Okay, so we have the relationship between the output variable and then the predictors, okay, which is based on the train set. Okay, we have our type, and this is C classification. Okay, our kernel here is linear, and we set our scale to false. Okay, now you will see some stuff here, the parameters. We'll talk about some of them. Okay, so here we have a cost parameter. We'll speak about it later. Okay, but the default figure is 1. And then notice something, that the number of support vectors is 55. Okay, so which means that we have 55 points in the data set that are very close to the decision boundary.
Decision.
All right. And it has an effect on the predictive capability of our model. So as much as possible, we want to reduce the support vectors. Okay. We want to reduce the support vectors so that the data points will fall clearly into each region. You don't want something that is very close to the decision boundary and you misclassify. All right. Yes, Christiana, I see your hand raised.
Please, sir, I'm not getting the fit model. Mine is not working. I don't know why.
Which one?
After
The
SB,
SVM.
yeah, your line 64.
Okay, so did you call the E1071 from the library?
Yes, sir.
Okay. And it's not working. Okay.
In formula, no data argument, error in terms, dot formula, something, plenty.
Hey, these people. Okay, let's check. Let's check. The errors are too many. Let's check and sort it out. Don't worry. Don't worry. Okay. So Christy, share your screen.
Please, sir, can you see my screen?
Yes. So I think it has a problem with the C classification.
No, I think that she closed the.
You close the argument line 71. Remove the bracket, and then good.
Please, like this.
And then the kernel is linear. Specify the kernel. The linear is in inverted commas. Okay. So spell linear.
I should spell, okay.
And then so bring a comma after the inverted comma. And then go down. And then specify the scale. The scale is equal to false. Okay. All right. So I think, yeah, it should be fine. So give it SVM model, the object name, line 70.
What is the name?
Yes, SVM model, SVM underscore model. Or give it any name that you want.
Okay. This one is okay.
Okay, yeah. And so run this. Okay, it's fine now. So now call the SVM model, and then you see so yours is the number of support vectors for yours is 57.
57.
Okay. So scroll up a bit so that you see it well, the number of things. I mean the quadrant. The quadrant itself, move the whole thing. You have very small space for your console. Move it up a bit. Yeah. Good. Good.
So I'm good to go in.
Yeah, you're good to go.
Thank you very much.
Okay, you're welcome. Right. So the main idea is to kind of reduce the number of support vectors. Okay. By the meantime, let's explore some of the
Hello, Nana.
Yes.
Please, can you explain the 55?
The 55 is the number of support vectors. Okay. So the number of support vectors I explained earlier on, as these points are very close to the decision boundary. Okay. And it might lead to misclassification. Meanwhile, too, they are very important. When you remove them too, it affects the position of the decision boundary. So as much as possible, you want to have as little support vectors as possible. Okay, without compromising the effectiveness of
Thank
the
you.
model too much. Okay. All right, good. So let's visualize our plot. Okay, so let's plot our X is equal to the SVM model. Our plot is equal to the SVM model. Okay, and then our data is the train set. Okay, let's plot it. Okay, we see our SVM classification plot. Now, where it is marked X, okay, where it is marked X, these are the support vectors. Okay, where it is marked X, these are the support vectors. So anywhere you see the X, these are support vectors. So now let's obtain class predictions for the test set. Okay, so let's predict. We want to use our SVM model against the test set. Okay. Test set. Okay. So what we do let's call this predict test. So let's run this. So let's check the accuracy of the model. Okay. So we use our pred test. And then compare it with our test set, the Y column, isn't it? And this. Okay, so that gives us a perfect model. Remember that this one was randomly generated. Okay, but you want to be as close to one as possible. Okay, so this is a perfect model, but we know why it is like that because of the because of how we generated it. Any questions?
Nana, I have a question.
Yes. Is that Nancy?
Yes, please.
Okay, please go ahead.
So you see how you put kernel is equal to linear?
Yes.
Does it mean you can feed it different, like
Yes. So here, we know from the word go, when we're doing the ggplot that S1 is equal to S2. So we know that it is linear. Okay. So you could have a situation whereby the data set is not linear. Okay, so we'll have a look at it and then see how we can apply SVM for that.
Okay.
Okay. Okay, so let's look at another model.
And please, one more question.
You say?
I know this, one more question.
Yeah.
I know what we did was just from a randomly generated data frame, and we are getting a perfect model. So if we have a data set with say 1,000 instead of 200 rows, can it survive?
Yeah, you can try it. You can change the n to 1,000 and just run it and then see. Okay.
All right.
And then see the result. Right.
Thank
So
you,
you're welcome. So let's build another model. Okay. Let's build another model and then change the parameters a bit. Okay.
Please, Nana, question.
Yes, please. Go ahead.
With regards to the number of support vectors,
yes,
is there an ideal number to have?
Not really. What I mean, if you have 0 support vectors, it's perfect. Have you seen? So the idea is to remove the support vectors. Remember that SVM might not be suitable for your data set. Have you seen?
Okay.
Hello. It might not be suitable for your data set. So for instance, if you reduce the number of support vectors and then still you try to remove them and still they are there, then that means that you are better off using another model to build your predictive model. Another application to build your predictive model. Have you seen?
Okay.
So in the best case scenario, you should have as little support vectors as possible, and then you can use that to make your prediction. Okay, so let's see. Yes.
I beg you. So then this SVM is not that versatile, even though you can use other
It's very,
forms
very
of.
versatile. It's very, very versatile.
But looking at what you are saying about the support vectors.
At least this one is giving you information about support vectors. Other models don't even have that capability to tell you that there are support vectors in your data set. Have you
That
seen?
is true.
And also SVM is flexible in the sense that it can be used for both linearly separable and also non-linearly separable.
It looks that way. It looks like it can even
So don't let the support vectors all that they are telling you is that when they are present, okay, you need to be a bit cautious. Okay. You don't want, the main thing is you don't want to misclassify. Okay. So the less support vectors you have, the less the probability that you misclassify a data point. Okay. So at least this one gives you information about how you can reduce your support vectors, and then you use it to do your prediction. Okay. All right. So let's see another model whereby we try and see if we can reduce the number of support vectors. Okay. So and one way to do that is to use our cost parameter. Okay. When we increase the cost parameter, it's able to deal with our support vectors. Okay. So let's see how we can apply that. Okay. Okay. So let me just copy this, what we had here. So we build a second model. Oh. So let's do this. Let's make it model 2. Yeah? Where is the cost? Okay. So here we didn't specify the cost. Okay, but you saw here, you saw in the output that the cost is set at 1. Okay, so that is the default value. So you can actually specify the cost. Okay, so let's specify the cost. Let's break a comma. Yeah. Let's say cost is equal to, let's choose 100. Let's run this. Also support vector 2. Okay. Do you see any difference? Do you see any difference?
Yes,
Yeah,
sir.
the support vectors is drastically reduced.
Good. All right. So it has in itself the mechanism to reduce the support. Okay. So when you increase the cost, okay, it's a tuning parameter. When you increase the cost, it deals with the issue of support vectors. Okay, to the minimum. So in this case, we are better off using model 2 to do our predictions, isn't it?
Yeah,
Instead
true.
of model 1. Okay. All right. Okay, yeah.
So Nana, please, what's the concept behind the costs reducing the support vector?
So it's a control parameter. Okay. So the cost is a control parameter. And as much as possible, so as the name is, if you remember too that if you reduce the support vectors are vectors data points that have a crucial influence on, so like they support your decision boundary, so to speak. Okay, so if you go to the extreme of removing all your support vectors, it might also not augur well for your model. So that is why when you increase the cost, okay, so it's like cost to you. Okay, when you increase the cost, you remove the support vectors. You might also want to check the accuracy of your model, okay, whether the model is improving or not improving. Because there are some instances whereby you could increase the cost, but your model will not be improving. So there is no point increasing the cost. Okay, so that means that you are, based upon the kind of data set you have, you are getting to the optimal level of the support vectors that you need to use. So the kind of data set that you have will determine whether the number of support vectors you have is okay or it is not okay. Okay. So when you increase the cost, you are actually removing some support vector, or you are actually removing some data points from your how do you call it? From your data set. So that is the downside. Okay. However, it improves your predictive capability. So when you say that 1 is in region A, it is there. You will not, the probability of you misclassifying that prediction is reduced because it is not very near the decision boundary. Have you seen?
Okay.
Mm-hmm. Yes. A couple of hands raised. Okay. Nancy, please go ahead.
Okay, Nana, I'm listening, but I'm getting a bit confused as well. If
Don't be confused.
you can, if you can increase the cost, and it's it's significantly, well, let me say, improving the data such that you have fewer data points close to the decision boundary. Then it's like with support vector, there is nothing like overfitting, because it's like you can just wipe them away.
But but there could be a cost. There could be a cost. You see, that's why we call it cost parameter. See, the support vector, all that we are saying is that the support vector plays a crucial element, plays a crucial role in the position of your decision boundary. All right.
Yeah.
So when you have so many support vectors, it is not the best because you can easily misclassify. So what the cost parameter does is that it reduces, as you increase the cost parameter, it reduces your support vectors. However, that is not the only way to check the fact that your support vectors has reduced. You should go ahead and also check the accuracy of the model, whether it is improving or it is not improving.
With the mean we did earlier, right?
Exactly, yes. So you do both of them together. Okay, so there could be instances, depending upon your data set, there could be instances where you increase the cost. It's not even having an effect on your support, on your accuracy of your model. Then there is no point increasing your cost. Okay, so you increase the cost up to, so you do it hand in hand and then check if there is improvement in the accuracy of your there's improvement in the accuracy of your SVM model, then that means that the increment in your cost is worth it. Okay. That is the idea.
Thank you.
Okay, you are welcome. All right, so here, you see the first one that we did, the accuracy was 100%. So let's check this time round too. Let's copy this one. So we need to copy this whole thing again. So now we are using model 2, yeah? So let's make this pretest 2 and then pretest 2 here. Okay, so this is still 1, okay? So it's giving a perfect model, but here we have, so you see that here, although we reduce the number of support vectors, okay, we increase the cost and reduce the number of support vectors. Our accuracy still stayed at 100%. Okay, so yeah, we can take later, probably when there's time, we can take other data sets, okay, and then apply. You could even apply the SVMs to the data sets that we've used for logistic regression and the HR stuff, and then the loan applications and stuff like that I sent to you. Okay, so you can do that and then see how it will also the predictive power of SVM will be in those circumstances. In those circumstances, I'm sure it will not give you 100%. Okay, it will not be, the accuracy will not be 100%. Okay, yes, Christiana.
Please say, I think reducing the support vector doesn't influence this particular.
Yes, that's what I'm saying. So here it still stays at 100%.
Yeah.
So that's a good observation. Okay. All right. Okay, so let's look at a situation where we are not dealing with a linearly separable case. Okay, which makes SVM very flexible. Okay, so let's deal with a situation whereby the data set is radially separable. Okay, like a circle. It's almost 3 already. Please, today we will not be having long breaks. So Okay. So let's finish this. We'll go for a short break and then we come. Okay. Let's try and cover as much as possible. I don't know how today will go, but anyway. Radially separable cases. So let's generate it. Okay, let's generate it. We are generating it ourselves. So let's set n to be, let's say 600. Yeah. So let's have another data set called df3. So we want to create a data frame. Okay, where our S1 is equal to random uniform numbers. We are taking n, but this time around, let's specify the minimum and then the maximum. So minimum equal to -1, and the maximum is 1. Then let's do for x2. So random uniform numbers. And we have our max. Our max, our minimum equal to 1. Then our maximum. Minimum is -1, sorry. Then
Another equal to for x2.
yes, yeah, thank you. Okay, run if. Yes, I think we are fine here. So let's create our circular boundary. Okay. Okay, so let's specify our radius. So, and then let's specify our squared radius. So let's square it. Where is my square? Yeah, it's here. Okay. So let's take our DF3 Y. Remember that we also have to create a factor. So the ones we have negative ones and ones, but this time around, it's either you are within the inner circle or outer the circle. Okay. So the same argument, if else argument we used earlier on. So DF3 x1, let's square it. Then we have 3x2. Let's square that one too. Okay. So if it's less than the radius squared, then it's negative. If it is above, then 1. Okay. And remember that this negative 1 and 1, we are factoring it. Okay, so let's wrap all this in a factor. Okay. So once we are doing this in a factor, let's specify the levels of the factor. So here we have negative 1 and 1. Let's close the bracket. Okay. So let's plot our data. When we finish this, then we go for a short break, okay? Then come. So let's ggplot DF3. Okay, our aesthetics. We have x1, and then y is equal to x2. Or we don't need a y, just bring s2. That also works. Then our color is equal to y. Okay, let's add a layer. So we want the data points. Okay, so we need the geom points. Okay, let's color them just like we did for the other one. So scale, color manual. Scale, color manual. Okay, let's specify the values. Okay, so in this instance, we have 1 for -1 for red. Remember, -1 for red, and then 1 for blue. One for blue. Okay, the blue should be inverted commas. Okay, so we name this P. So it's run P. run into problems here. X1, X2,
Nana, the negative one should be equal to no comma.
Yeah, I've just seen it. Okay, thank you. Okay, so let's run it. So you can see here that this a radially separable data set. Okay, so you have some points that are within, so it's like you have one that is round outside, and then the black one is an inner circle within. So if this one you are going to use, you cannot basically use what we call a linearly separable case in order to work this. Okay, so that's a difficulty here. So let's add a circular boundary to it. Okay. Please, are we all getting the same information?
No, sir.
Okay.
Please, sir, I'm not.
Okay.
It seems I missed something at if you
Right.
move up a little.
Okay.
Where the square radius, is it radius square?
Okay.
Seems I missed something about
So set your radius to be 0.7. Okay.
Please, I'm there. I've done that.
Okay, and then you square it. Have you squared
Yes,
it?
I've done that. Yes.
Okay, so just do the if else. Do this one.
That's where the problem is.
So take the if else and then take the data set DF3. DF3 and then
yes, I've done that.
And then square the S1. Plus
I've done that one too.
DF3 and then DF3 to S2 and then square that.
That's where, okay. Please, can we continue that one? That's fine. Seems I'm still not done.
Okay. So less than the radius squared. If it is less than the radius squared, then it should be -1. If it's not -1, then it is 1. Okay.
I've done that side too.
You've done that too. So specify the levels. So have you factored it? So wrap
Yes, I
everything
did
into the
factor it.
factor. Okay, and then bring the levels. Okay.
I'm having, so I still have issue with the factor.
The
I don't know.
else.
Yes,
If
after the
else,
factor,
okay. So
there's a bracket, open bracket.
share your screen. Let me see what you have there. Probably you have something.
Come on.
Okay.
Yeah, where the cursor
Yes.
is.
No, that place is fine. You see where you have the levels.
Yes, yeah.
You see where you have the levels.
Yes, sir.
So you should close the brackets. Remove the dot, the comma from after
The comma.
Yes. And then close the bracket.
Please, like this.
Yes. Okay, so run it again. Let me see. Run 113. 113. Run. Okay, so first of all, run 111. Let's see. Okay. Run this one too. Okay, so run 113. Yeah. And then wait. After you've done this, you ggplot df3, and then aesthetics is equal to s1, s2, and then you add a
Values is equal to C.
So the values is equal to, not minus. Okay. 119.
Okay. Please, am I okay?
Yes, you should be okay now. Yeah. We'll run it again.
Thank you, sir.
Good. Good. So you can see that this is not a linearly separable case. Okay, so this is a radially separable case that we are having. Okay, you can see from the data. Okay, it's round. Okay, so in that case, how do you do the prediction? Okay, so that's what we have here. Are you seeing my slides?
No, it's still R.
It's still R. Yes, NS. NS, you have an issue.
Yeah, Nana,
Yes.
I'm not getting the graphics.
Oh, okay. The ggplot is not coming.
Yeah, it's not working.
Okay. All right. So, okay, share your screen. Let me see something. Let's see where you are having an issue.
This one.
Okay. Were you okay with line 110?
Yeah.
110 down. Were you okay with it? Everything fine. No errors.
Gives me error.
So the error, well, your font is very small. Okay, so let's see. So factor if else, this plus this plus reduce. Shouldn't it okay, so you have -1 and then 1 and then the levels. Okay, so run 117, let's see. That one ran.
Yeah, ran.
Okay, so you have ggplot, df3, aesthetics, jump point, go down a bit. Values is going to see. Everything seems okay here. But the other plots, it plotted fine.
Oh yeah. I go for the other.
Okay. I think we are
So do I have to go ggplot again?
Okay, you call it from the library again. Let's see. So that we are sure. Okay. Invalid.
Can you try increasing the quadrants where the plot is supposed to be? Just make it bigger. And then try it again.
Okay. So you send it a bit to the left so that we can see the code. Not too much, but okay. Let's see. Everything seems okay. EF3. Okay. let's do it like we did for did you bring the levels? Okay, so
Yeah.
let's do it like we did for, let's break them down. So bring a comment to 125. And then run this one alone. Let's see. Okay, so it's coming from this side. Okay. X1, X2, color. Okay. What does the error say? What does the error say?
Error in .core.graphics. See palette to and invalid graphics state.
Yeah, or someone say something.
Yes, I was saying that you can try running something to reset your graphics device. Sometimes that might be the issue. I think I posted something in the chat.
Okay. Then see, or if you want, you can just close this session, come back, and then restart it and then run it. Okay.
All right, I'll do that. Thank you very much. Let me stop sharing so you can continue.
All right, that's fine. Okay, so